gas laws. So STP, that's the standard conditions for your temperature and pressure. You can find this on your chemistry reference table. So at STP, the pressure is going to be 1 atmosphere ATM, or 101.3 kPa, or 760 mmHg, or 760 torr. So these are all equivalent. That means 1 ATM is equal to 101.3 kPa. So you can convert between these in your calculations. At STP, temperature is going to be 0 degrees Celsius, or 273 degrees Kelvin. So you can convert between 0 degrees Celsius to 273 degrees Kelvin. And the volume of 1 mole of any gas is 22.4 liters at STP. The ideal gas law. So the volume V occupied by n moles of any gas has a pressure P at temperature T in Kelvin. This relationship for the variables is PV equals nRT. So this equation, PV equals nRT, that's our ideal gas law. So we use this to solve for either P pressure, V volume, N moles, or T temperature. So we use the gas constant R in this ideal gas law, PV equals nRT. So the units for R, they correspond with the unit of pressure that we're using in the equation. So for example, if we're using ATM, we would use 0.0821 for R, or if we're using mmHg for pressure, we're going to be using 62.4 for R. Volume. So it's always going to be in liters. So if it's in milliliters, you want to convert to liters. And 1 mole of any gas would occupy 22.4 liters of volume only at STP. So the moles. If your moles, you use the moles to get N. So if they give you in the substance in grams, you want to convert that to moles using molar mass. And the temperature T, that always is in Kelvin. So that means if they give you your temperature in Celsius, you want to convert it to Kelvin by adding 273 degrees to whatever degrees Kelvin or whatever degrees Celsius that you have. So for example, if you have 25 degrees Celsius, you want to convert that to Kelvin, you would take 25 and you'd add 273 degrees to it to get 298 degrees Kelvin. For example, so an 18-liter container holds 16 grams of oxygen gas at 45 degrees Celsius. What is the pressure in the container in atmospheres? So you'd use the ideal gas law, PV equals nRT. So you can rearrange the ideal gas law to fit whatever you're solving for. So since we're solving for pressure in the container, we're going to rearrange the equation algebraically to have P equal nRT divided by V. So to get our N moles, we could take the 16 grams divided by the molar mass of our oxygen gas. So our oxygen gas is O2, so the molar mass of that would be 32. So 16 divided by 32 is 0.5, and that's the number of moles of oxygen gas that we have. So our T, it's 45 degrees Celsius. We need to convert this to Kelvin, so we add 273 degrees to it to get 318 degrees Kelvin. And our R, so since the pressure is an ATM, we would use 0.0821 as our R. So in the PV equals nRT equation, we plug in these variables to get P equals 0.5 times 0.0821 times 318 divided by 18. So our P would equal 0.725 ATM. So how many moles of oxygen must be placed in a 3-liter container in order to exert a pressure of 2 atm at 25 degrees Celsius? So again, we use the ideal gas law, PV equals nRT, and we can rearrange this to have N equal PV divided by RT. And here we just plug in the given variables. So we have that the P would be 2 atm, the V would be 3 liters, and then the R, since it's an atm, we have to use 0.0821, and the 25 degrees Celsius, we have to convert that to Kelvin by adding the 273 degrees. So you just plug this in your calculator, and you get the N to equal 0.245 moles. So the combined gas law, that's the ratio between the pressure volume product and the temperature of a system, remains constant. So the P1 times V1 over T1 would equal P2 times V2 over T2. So we use the given information in the problem to solve for the unknown variable, which could either be the P, V, or T. So for example, a sample of sulfur dioxide occupies a volume of 652 milliliters at 40 degrees Celsius and 720 mmHg. What volume will the sulfur dioxide occupy at STP? So we have our PV over T equals PV over T equation. So we plug in the initial variables, so it'd be 720 mmHg as the pressure. The volume would be 652 milliliters, but we must convert that to liters, so it'd be 0.652 liters divided by the temperature. The temperature is 40 degrees, but we must convert that to Kelvin, so we add the 273 degrees to that. And then the other half, the P2 times V2 over T2, that would be 760 mmHg, which is the STP for pressure, times our unknown volume, and then the temperature at STP, which would be 273 degrees Kelvin. So we plug this in our calculator, we solve for V, and our V would equal 0.539 liters. So that means at STP, that sample of sulfur dioxide would occupy 0.539 liters. So 322 liters of hydrogen occupies a volume of 197 liters at STP if the initial temperature of the hydrogen was 73 or 37 degrees Celsius. What was the initial pressure? So we use the PV divided by T equals PV divided by T. We plug in the given information, so it's P times the 322 liters of hydrogen divided by 37 degrees Celsius converted to Kelvin, and that's going to equal 1 atm times 197 liters divided by the temperature at STP. So we solve for P, and that would come to 0.695 atm. So Dalton's law of partial pressure. So that's the pressure exerted by an individual gas in a mixture that is known as partial pressure. Assuming we have a mixture of ideal gases, we can use the ideal gas law to solve problems involving gases in a mixture. Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So the pressure of the total would equal the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and etc. So it would pretty much equal the pressure of the total gases would equal the sum of everything combined. So example, a container contains 3 gases N2O2, and argon gas, with partial pressures of 23.3 kPa, 40.9 kPa, and 13.7 kPa respectively. What is the total pressure inside the container? So we have the given information of the pressure of each of the partial pressures of the gases, and with the Dalton's law of partial pressures, we can combine all these gases, and with the sum of this, we get 77.9 kPa, and that would be the total pressure inside the container.